Welcome to G Fun Facts Online. Today, we are dissecting a fundamental reimagining of the physical world's operating system, the dawn of the zero-labor era. For decades, robotics has been confined to the rigid cages of industrial assembly lines. These machines were structured, predictable, and blind to the nuances of reality. A traditional robot could weld a car door with sub-millimeter precision, provided the door was in the exact same spot, down to the micron, every single time. Move the door an inch, or swap it for a different model, and the machine would fail, often catastrophically. But today, we are witnessing a tectonic shift. We are moving from automation, which is simply the repetition of pre-programmed tasks, to autonomy, the intelligent negotiation of unstructured chaotic environments. This is the age of dexterous manipulation in unstructured environments, a technological frontier where robots are learning to peel fruit without bruising it, fold laundry in a cluttered bedroom, and repair satellites in the vacuum of space. To understand the magnitude of this revolution, we must first confront Moravec's paradox, formulated in the 1980s by researchers Hans Moravec, Rodney Brooks, and Marvin Minsky. This paradox observes a counterintuitive truth about artificial intelligence. High-level reasoning requires very little computation, but low-level sensory motor skills require enormous computational resources. In simpler terms, teaching a computer to beat a grandmaster at chess is relatively easy. Teaching a robot to walk across a messy room or tie a shoelace is agonizingly difficult. This paradox has been the primary bottleneck for robotics for 40 years. Traditional robots are position-controlled. They move from coordinate A to coordinate B. But the real world is not a coordinate system. It is a messy, dynamic flux of soft objects, changing lighting, and unpredictable obstacles. A zero-labor robot cannot just follow a path. It must perceive its environment, reason about physics, and adapt its actions in milliseconds. We define an unstructured environment as any setting where the layout is not known a priori or changes dynamically. Consider your own home, a living room with scattered toys, a sleeping cat, and lighting conditions that shift from dawn to dusk. Or consider a farm, an orchard where every branch grows differently, wind moves the leaves, and fruit varies in ripeness and softness. Even a disaster zone, like a collapsed building where rubble is unstable, represents this chaotic complexity. In these environments, a robot needs dexterous manipulation. This is the ability to perform complex, contact-rich tasks with hands or end effectors. It goes far beyond simple pick-and-place operations. It involves sliding, rolling, and reorienting objects within the hand, known as in-hand manipulation, and modulating force to handle a steel wrench or a raw egg with equal competence. The breakthrough that has unlocked zero-labor robotics in the mid-2020s is the convergence of three distinct technological pillars, often described as the brain-cerebellum-body synergy. Let's start with the brain. The brain of the new robot is no longer a static codebase, but a dynamic AI model. The explosion of large language models and vision language models has birthed robot GPTs. Unlike old robots that saw pixels, these systems see concepts. A vision language model-equipped robot doesn't just see a brown blob. It identifies a wilted apple and infers that it should probably not pick it. We are also seeing the rise of large action models, or LAMs. These are AI models trained not just on text or images, but on trajectories of movement. By ingesting millions of hours of video of humans performing tasks, models like Google DeepMind's Aloha Unleashed have learned to generalize skills. A robot taught to pick up a red cup can figure out how to pick up a blue mug without retraining. Furthermore, we have solved the reality gap through sim-to-real transfer. Reinforcement learning allows robots to practice a task billions of times in a simulated physics engine, like NVIDIA's Isaac Sim, before ever moving a physical muscle. By 2025, algorithms mastered the ability to transfer this synthetic muscle memory to the real world with near zero adaptation time. The second pillar is the cerebellum. If the brain decides what to do, the cerebellum handles how to do it. This involves high-frequency feedback loops that keep a robot from crushing a wine glass. The missing link here has been haptic feedback. New sensors from companies like BrainCo and GelSight provide high-resolution tactile maps, allowing robots to feel texture, slip, and hardness. This data is fed into the control loop, enabling reflexes. If an object starts to slip, the robot tightens its grip instantly, faster than a human could react. This is coupled with active perception, where robots move their cameras to peer around occlusions, finding a grasp point on a hidden fruit or tool. The third pillar is the body. The hardware has finally caught up to the software. We have moved beyond simple pincers to multi-fingered dexterous hands with over 20 degrees of freedom, like those from the Shadow Robot Company or Tesla's Optimus. But rigidity is often a liability. Soft robotics has emerged as a crucial field. For instance, MIT's RoboGrocery project introduced soft, silicone-based grippers that conform to the shape of an object. These grippers use air pressure or fluid dynamics to gently envelope a peach or a bag of chips, providing a secure grip without localized pressure points that cause bruising. This theoretical framework is fascinating, but the application is where the zero-labor economy becomes tangible. 4 sectors are currently undergoing a radical transformation: agriculture, logistics, manufacturing, and the home. Let's look at agriculture first. Farming is the ultimate unstructured environment. No two apples are alike, and the ground is never flat. Yet, the agricultural sector faces a desperate labor shortage, projected at over 2 million workers globally by 2030. This is driving a rapid shift to zero-labor farming. Startups like Nanovel have deployed AI-powered citrus pickers. These are not simple shakers. They are multi-armed robots that use advanced computer vision to identify ripe fruit inside dense foliage. They extend telescopic arms, use a vacuum gripper to cradle the fruit, and a cutter to snip the stem, replicating the delicate motion of a human hand. Simultaneously, companies like John Deere and Monarch Tractor have deployed fully autonomous tractors that do not require a driver in the cab. These machines use stereo cameras and AI to distinguish between crops and weeds, tilling, planting, and spraying day and night. This shift decouples food production from labor availability. A zero-labor farm can harvest at the exact moment of peak ripeness, regardless of whether it's 3 a.m. or a national holiday, significantly reducing food waste and increasing yield. In logistics and retail, the holy grail has always been piece-picking. Warehouses have long been automated for moving pallets, but reaching into a bin of random items and packing them into a box remained a human task until now. Amazon Sparrow represents a major leap forward. It is a robotic system capable of detecting, selecting, and handling millions of individual products using a suction cup array and computer vision. It represents the shift from macro-logistics to micro-dexterity. Similarly, in the UK, Ocado has pioneered a hive-mind warehouse with their on-grid robotic pick system. Sitting atop a massive grid of moving bins, robotic arms utilize deep reinforcement learning to pick tens of thousands of grocery items. The system uses behavioral cloning, watching human pickers to learn how to handle complex items like a net of oranges versus a rigid box, and then refines that skill, addressing the handling of delicate items. MIT's robo-grocery innovation uses soft sensors to distinguish between a crushable loaf of bread and a heavy can of soup, creating a packing strategy on the fly that places heavy items at the bottom, a cognitive task previously exclusive to humans. In manufacturing, we are seeing the evolution of the lights-out factory. While Fanuc in Japan has operated a lights-out robot building factory since 2001, the concept has evolved in 2025 from mass production to flexible production. The new generation of factories, like Xiaomi's smartphone plant or Gree's 5.5G factory, handle high-mix, low-volume production. Mobile manipulators roam the floor, changing tools and reconfiguring assembly lines on the fly. Robots are now capable of complex assembly tasks, like threading a wire through a small hole or snapping a flexible plastic clip into place, tasks that rely heavily on tactile feedback. These factories are immune to pandemics, labor strikes, and skill shortages, offering production consistency where defect rates drop to near zero. Perhaps the most personal application is in the home. At CES 2026, LG Electronics crystallized this with their zero-labor home vision, headlined by the CLOID robot. Unlike a vacuum that blindly bumps into walls, CLOID and competitors like Samsung's Bally or Tesla's Optimus Gen 3 are mobile manipulators. They can load a dishwasher, pick up laundry, and pour a glass of water. LG coined the term affectionate intelligence to describe AI that understands context. It knows not just how to wash dishes, but when to do it so as not to disturb the homeowner. It recognizes that a child's toy is precious and should be placed on a shelf, not in the trash. Recent breakthroughs in vision language action models allow these robots to reason about clutter. A robot can now process a chain of thoughts such as, to pick up the sock, I must first move the chair. This transition to zero-labor robotics is a socio-economic earthquake. The primary driver is labor scarcity, not just cost-cutting. By 2030, the global manufacturing and logistics sectors face a projected shortage of over 2.1 million workers. In agriculture, the average age of a farmer in the US and Japan is nearing 60. There are simply not enough humans willing to perform dull, dirty, and dangerous jobs. Automation allows for super productivity, where robots improve with every software update, potentially adding trillions to the global GDP. The narrative of robots taking jobs is shifting to robots changing jobs. The role of the human worker is evolving from manual manipulation to supervision and orchestration. We are seeing the rise of remote pilots. In Ocado's warehouses, if a robot encounters an exception, it pings a human who clicks on the grasp point on a screen. The robot executes the move and learns from the interaction, meaning the human only has to solve that specific problem once. We are also seeing a new class of blue-collar jobs called robot wranglers, technicians responsible for maintaining the fleet and managing the physical-digital interface. However, significant bottlenecks remain. Power consumption is a critical limitation. Running massive AI models requires immense energy, creating a compute versus endurance trade-off for battery-operated robots. Latency and bandwidth are also hurdles. For telesurgery or remote orchestration, even a 50-millisecond delay can be catastrophic, making 5.5G and 6G networks a prerequisite. There is also the issue of data scarcity. We have trillions of tokens of text to train language models, but we lack a comparable dataset for physical interaction. Collecting high-quality data of robots failing and succeeding in the real world is slow and expensive. Finally, safety and ethics remain paramount. As robots become more autonomous, ensuring value alignment is critical to prevent bad choices based on biased data or cultural misunderstandings. Looking ahead to 2030 and beyond, the distinction between digital and physical tasks will blur. We will likely see an app store for Matter, where developers write skills for robots just as they write apps for phones. A developer in Prague could write a folding a fitted sheet algorithm and sell it to millions of robot owners worldwide. General-purpose humanoid robots may drop in price to comparable levels of a small car, making them viable for small businesses and nursing homes. The ultimate promise of zero-labor robotics is the return of time. Just as the washing machine freed households from hours of manual scrubbing, the next generation of robots promises to free humanity from the remaining physical drudgery of survival. Zero-labor robotics is not about erasing human effort. It is about elevating it. By solving the challenge of dexterous manipulation in unstructured environments, we are building a world where machines handle the what is, so that humans can focus on the what could be. The easy problems of the physical world are finally becoming easy for our machines, unlocking a future of unprecedented abundance and creativity.